All right. Hello and welcome to another physics video lecture. Today we are going to be talking about heat and temperature. I want you just to sit there and ask yourself a question real quick. Here's the question. What makes something hot or cold? I mean, hot and cold objects are something that you encounter every single day, but you ever stop to ask yourself, well, what makes it hot or cold? Is it in the nature of the object itself? Not really. I mean, think about water. Water can be boiling, or it can be frozen, or it can be in between. And the same is true of literally anything else. So what about that object makes it hot or cold? Now, the answer to this question is going to go back to something that we're going to be talking about for the rest of this semester. In order to answer these questions like what is heat, or what is electricity, or what is magnetism, or where does nuclear energy come from, okay? The way to answer those questions is we have to go down and look at the atoms of the object, all right? And in the case of heat, or excuse me, of something being hot or cold, okay, it comes down to what those atoms are doing, specifically how fast they are moving, all right? And it's as simple as this. If something is hot, that means that its atoms are moving really quickly, right? They're vibrating really fast and they're bouncing off of each other. If something is really cold, the atoms vibrate really slowly. And again, going back to water, this is why when water gets hot, it turns to steam. The atoms in hot water are bouncing off of each other so fast that they start moving away from each other. And the farther they move away, okay, the lighter it gets and you get steam. Similarly, when you have ice, okay, the water's getting colder, those atoms start to slow down, they vibrate slower, they get closer, and the closer they get, the more solid they become, okay? So this is kind of cool, right? This is something that I would like for you to take with you from this class. If anybody in the future ever, for whatever reason, asks you why something is hot or cold, you simply say, it depends on how fast the atoms in that object are moving, okay? And it's true for everything. All right. So to talk about heat and temperature, the place we're going to start is actually with talking about temperature. Now, what is the temperature of an object? All right, well, you could probably easily say the temperature of an object is how hot or cold something is, and you'd be correct. But we're going to take it a step further and apply our new definitions of hot and cold to this definition, and what that gives us is that temperature is the measure of the average kinetic energy of the atoms in an object, okay? Sounds fancy, but it's actually simpler than what you might think. All we're saying here is if you take all the atoms in an object and you measure their kinetic energy, and remember, kinetic energy is just their movement, that would tell you the temperature of the object. Now, why do we measure the average kinetic energy? Well, all of the atoms inside of an object, all the hundreds of billions of trillions of millions of gazillions of atoms inside of an object, I did make up that number, but all of those atoms, they're not all moving at exactly the same speed, but you can take the average, okay, and find that. And that number, that amount of movement, that speed is the object's temperature, right? Because remember, hot objects have very fast moving atoms, cold objects have very slow moving atoms. How do we measure temperature? Well, I'm sure you know. You're probably used to measuring things in degrees Fahrenheit, but this is science. We're using the metric system, so we're using degrees Celsius. I have a little chart over here. I'm not sure if you can see it, but you can download this PowerPoint. The reason we use Celsius is because it's simpler than Fahrenheit. Let me show you why. In Celsius, in Fahrenheit, I'm sure you know, water freezes at 32 degrees, which we experienced last week, and water boils at 212 degrees Fahrenheit. That's weird. Those are weird numbers. In Celsius, water freezes at 0 degrees, and it boils at 100 degrees, all right? It's just a smoother, easier system, and it's the one that we use in this class, okay? All right, so that's temperature. Let's think about something real fast. Let's think about a nice, delicious cup of coffee, something that I love dearly. If I took this cup of coffee and put it on the countertop and just left it there, what would eventually happen to that cup of coffee? That nice hot cup of coffee would eventually get colder, right? I mean, this is not news to anybody. But again, my question to you is why? Why does the hot cup of coffee get colder? Okay? And the answer, again, is in the atoms. So what's happening to these atoms? Well, you got to remember that atoms are always bouncing into each other, okay? So if we look closer to this cup of coffee, what we would see is we would see that inside the cup of coffee, we have these hot, fast-moving atoms, and they're flying all over the place super fast, okay? Outside, in the air, we have colder, slower-moving atoms, right? Now, if you go back and remember what we talked about when we were talking about collisions, remember, momentum is always conserved. So when these atoms of the coffee are smacking into the atoms that are in the air, okay, it's like hundreds of trillions of little pool balls smacking into each other. Remember, when one pool ball hits the other, boom, it causes it to speed up. And that's what's happening here, okay? When the hot, fast atoms of the coffee hit the colder, slow atoms of the air, they give them their momentum, okay? This is why when you hold your hand above a hot cup of coffee, the air above the hot cup of coffee itself feels hot, okay? The atoms in the coffee are hitting the atoms in the air, and like those little tiny pool balls, they are speeding those atoms up, okay? This is what is happening, okay? And this interaction of fast-moving atoms smacking into slow-moving atoms is what we call heat, okay? Now again, heat is a weird thing to put a definition to, but I tried to make it as simple as I can, okay? What is heat? Heat is the transfer of energy between two objects with different temperatures, all right? So again, sorry about the squeak. Again, objects that have high temperatures have these super fast moving atoms that are all over the place, and objects with low temperatures, okay, have slower moving atoms going between them, all right? Well, again, what's happening is those fast atoms smack into those slow atoms, okay? And that causes the fast moving atoms to slow down, and it causes the slow moving atoms to speed up. We call this the energy of molecular motion, okay? What that means is again, heat is all about the transfer of energy from fast atoms to slow atoms, okay? It's also called thermal energy. So for the rest of the year, you're gonna hear me talking about thermal energy. Whenever you hear that, you know that I'm talking about something to do with heat and temperature, right? And I'm sure you probably know this word before. You've heard of a thermostat, or a thermometer. Those things measure and control temperature, and they measure and control heat, which is the transfer or the raising or lowering of temperature, okay? So something that is very, very important to understand, okay? When we talk about, let's say, that hot cup of coffee, let's say this is our hot cup of coffee, this is our colder air, okay? A lot of people will say, let's say I'm holding a cold ice cube in my hand, okay? That ice cube makes my hand feel colder, right? So a lot of people will say that there's cold energy going from the ice cube into my hand, all right? And I want you to know from here, forever, that there's no such thing as cold energy, okay? It just doesn't exist, right? The way that heat moves is heat always moves from warmer objects to colder objects, always, okay? Heat is an energy of movement. It's the energy of those atoms moving, okay? You can think about heat and cold the same way that I think about light and dark. If I turn off the lights in the room, okay, I didn't add darkness to the room. I took away the light. Darkness is the absence of light, okay? Cold is the absence of heat, right? So, and this takes a second, okay? But if you take your nice warm hand and put a cold ice cube in it, okay? The ice cube is not putting cold into your hand, although it feels like it, okay? Your hand, okay, the atoms in your hand are hitting the ice cube, and that's causing the atoms in the ice cube to speed up and melt, but it's also taking away the heat that's in your hand, okay? So the heat from your hand is going into the ice cube, not the other way around, okay? And again, underline this, you can highlight it if you have it. Heat always moves from hot objects to cold objects, okay? There's no such thing as cold energy, all right? Cold is what happens when you remove heat, okay? That's why space is cold, because there's no atmosphere for the to be heated up by the sun, warmed by the sun, all right? Okay, so thermal equilibrium. Ooh, big fancy word. I love these, all right? So whenever you see big fancy words, and we're gonna see a lot of them this semester, I like to break them down into smaller parts, right? Now, we've already seen the word thermal, and we know that that has to do with temperature, right? Like a thermometer, right? It measures temperature. Equilibrium. This is a word we're gonna see a few times for the rest of the year. It's a good word to know, all right? Now, if you're looking at this, hopefully you already know what equilibrium means, but if you don't, I like to break it down into smaller parts. Specifically, those first 5 letters right there, right? And as you can see, those first 5 letters look a lot like the word equal. So what we have here, okay, is equal temperature. And that's what thermal equilibrium means. It means that 2 objects have the same temperature. Okay? Now, the fancy science way of saying this is that the atoms in the objects are moving at the same speeds, right? So if you have 2 objects sitting in the same room for long enough, for example, the air in the room and that cup of coffee we talked about, eventually those 2 temperatures, right, the heat transferring between them is going to balance out, right? And this is what you're seeing right here. Here you have a hot object, here you have a cold object. Eventually they're going to balance out and they're going to become the same temperature, which is what we like to call room temperature. Pretty cool, right? Okay, so when you have thermal equilibrium, that means that the 2 objects are the same temperature, okay? And if they're the same temperature, that means their atoms are all moving at the same speed, which means that there is no heat flowing between the 2 objects. Remember, heat only flows between objects of different temperatures. You with me? Good. If I didn't say so earlier, this is a very, very important lesson to take down some notes. There's not that many, so make sure you're writing these down, okay? All right, so you are going to see problems that ask you to calculate thermal equilibrium, which sounds difficult, but it's not. Let me show you a question and show you how to answer it. If I take equal amounts of a hot water, let's say that's at 80 degrees Celsius, and a colder water that's at 60 degrees Celsius, okay? When those 2 temperatures finally even out, what is the final temperature of that water going to be? Now, you may be looking at this and you're like, well, you didn't give us an equation. And you don't really need an equation for this. All you got to realize is that there are equal amounts, okay, of both hot and cold water, okay? And that what's going to happen is the hot water is going to get colder and the cold water is going to get hotter, right? They're going to go like this until they meet in the middle. So you need to find the number that is in between 80 and 60. Okay, now how do you do that? All you got to do is find the average. When you find the average of 2 numbers, you're finding the number that is directly between the 2 of them. That's what an average is. Okay, so this is actually super simple. Hopefully you remember how to find the average of 2 things. If you don't, I'll show you. To find the final temperature, all you have to do is add up the 2 numbers and divide by the total amount of numbers, which in this case is 2. So to find the average temperature that these are going to end up at, you add 80 plus 60, which is 140, and 140 divided by 2 gives me 70. Looks fancy, pretty simple stuff, right? Okay. So the last thing we need to talk about is how heat can transfer from one source to another, okay? And there are actually 3 ways that heat can be transferred between 2 objects, all right? You've probably heard these words before, but we're gonna break them down. The first one is called conduction, all right? Conduction is heat transferred directly between 2 objects by those 2 objects touching, okay? This is the simplest method of heat transfer and the one that you probably think about the most. Conduction is when a hot object touches a cold object, right? Those fast moving atoms in the hot object hit the slow moving atoms in the cold object, okay? And heat's transferred from the hot to the cold. Examples of this, a steak in a frying pan. The atoms in this frying pan are rip-roaring hot, okay? You put a cold steak in there, and those hot atoms in the pan are gonna speed up the atoms inside of the steak and cause it to cook. I do love me a well-cooked steak, okay? So again, whenever you think of conduction, think of this, yo! All right? You got a hand, which is normal temperature, touching a super hot pan. If you touch a hot pan, that is conduction. That is you touching the heat, okay? If they're touching, it's conduction. Method number 2, convection. Now this is a word you might see maybe somewhere in your kitchen. What is convection? Convection is when heat is transferred through fluids. This is a great word. If you don't know what a fluid is anything that is not solid, meaning it is either a liquid or a gas, all right? Now, in order to understand convection, you need to understand this basic principle, okay? Hot or warm fluids always rise, whether they're water or gas, liquid or gas, right? And cold fluids always sink, or they always fall. Now, if you want to know why this is, it's because as atoms get hotter, they vibrate faster, and the faster they vibrate, the farther they get away from each other. The farther they get away from each other, the lighter they become, and voila, they rise up, right? But what happens as they rise up is they're getting farther and farther away from that heat source, which means they get colder and colder and slow down. And as they slow down, they get closer and closer, which makes them heavier, so they fall again, which causes them to heat and rise back up, which causes them to cool and fall back down. And this is why water boils. This is why you see all those bubbles in boiling water. There's steam escaping, but there's hot water going up and cold water going down. It's called a rolling boil, okay? So again, examples here are boiling water, which is easy to see, but this is also how ovens work. You may see that word on an oven where you'll see it say that it is a convection oven. And what that means is that there is warm air rising and cold air falling like this. Funny enough, this is also how we heat our houses, all right? Interestingly enough, there is a difference in architecture between houses in the south and houses in the north, okay? In the north, you will oftentimes see that the heating elements, like your heat, is found on the ground, right? You'll see vents on the ground, okay? And this is because it gets colder more than it gets hotter in the north, especially the far north, right? So they usually use their heat more than their air conditioning. So if you are using your heat more, you want the heat to come out of the ground and rise up to fill the whole room before it falls back down, right? Whereas here, where it's hotter more often than it's colder, we in Texas usually use our air conditioners more than we use our heaters, which is why in many houses, you'll see your heat vents in the ceiling. That's because you want your air conditioning, which is heavy and cold, to fall and fill up the whole room before the room heats it back up and it rises again. Just kind of a fun fact, right? Okay, next up, examples. Again, boiling water, okay? Whenever you boil pasta, this is convection, okay? The pasta is not directly touching another solid. It's not solid on solid. It's solid in a liquid. Or if you're roasting a chicken or baking bread in the oven, okay? It's not solid on solid. You're using the air around it to heat it up. That's convection, okay? And last but not least, we have radiation, okay? Radiation is the dangerous sounding one, and sometimes it is, not all the time, but sometimes, okay? And radiation is heat transferred through something called electromagnetic waves. Woohoo! Big word. Now, these are something that we are going to study in detail in the upcoming weeks, okay? But for right now, I just want you to know that electromagnetic waves include things like microwaves. They include things like infrared waves, which is heat. That's what we feel coming off of the sun, or infrared waves. This also includes the UV radiation that can cause you to get a sunburn or sometimes skin cancer. This also includes really hardcore radiation, things like X-rays, gamma rays, all right? But anytime you're talking about electromagnetic waves, you are talking about radiation, all right? And again, examples are microwaves, heat lamps, okay, and the sun itself. So microwaves. Also, the lovely gamma rays that make the Hulk, right? Here, we need to know that sometimes there's a combination of all three going on, okay? So for example, I'm a big fan of, oops, I took out the picture, of grilling steaks, okay? And whenever you grill or cook open an open fire, you're going to have all three of these things going on at once. So you have the fire, okay? And you have radiation in the form of infrared heat waves coming off. So you have radiation coming off. You then have the boiling water inside of the pan, okay? This is a fluid. The hot water rises, the cold water falls. This is convection right here. And then if you are not wearing a glove, okay, and this pan gets too hot, you touching the pan, this is direct contact of solid on solid, and that gives you conduction, all right? Now, a little fun fact about this is that some objects are better at transferring heat than other objects. Now, if you have tile in your bathroom and you wake up on a cold night and you walk into the bathroom, you might think that that tile floor is a lot colder than your nice warm hardwood floor or carpeted floor, but it's not true. Everything in that room is room temperature, okay? It's all sitting there. All of those atoms have bounced off of each other. So everything in your house, in that room, is actually the same temperature. It's just that some things are better at conducting heat than other things, which is why if you go into a room, or if you're in a classroom, this is a great example. If you touch the top of a desk, the wooden part, and the bottom of the desk, which is usually metal, the metal will feel colder. It's not colder, it's just better at taking that heat energy out of your hand, which makes it feel like it's colder. Just a fun fact, okay? All right, guys, that's it for today. Use this to answer the questions in your DOL, and as always, if you have any questions, shoot me an email, okay? Be good, guys.